So now let's move on to the next concept, which is the process of assigning values to variables and parameters. To evaluate the coordinates of a point on our ellipse, it is necessary to assign numerical values to the semi-axes and the parameter. A mathematician might say, we let a equals 2, b equals 1, t equals pi over 4, which is another usage of the symbol equals. If we executed statements like this in Mathematica, the result would be disastrous, because such an assignment would actually change the definition of the vector-valued function by replacing the symbols a and b by the numbers 2 and 1 respectively. But instead, Mathematica provides a construction for assigning temporary values of parameters and variables using this kind of statement. Parset, so this is an object which sets values of our parameters, and the construction is a goes to 2 and b goes to 1. So we've executed that, and to see the effect of that, we apply that to our vector-valued function and put the result in points. And we do that with this construction here. So this says replace the variable or the symbols in RVec by the values in this object parset. Quite a different process, and you can see the result is a vector-valued function of t in which the parameters a and b have been replaced by the values we want them to have. Now, because of the 2 pi periodicity of the trigonometric functions, these points move one revolution around the ellipse as the parameter changes. T changes from 0 to 2 pi, which can be used to define the endpoints of the domain of the vector value function by this. So this is a name, endpoints, fairly intuitive, and it assigns the values 0 and 2 pi. So we now have enough information to visualize our ellipse, and we do this. There's using the Mathematica function parametric plot, which is a plotting routine where our function is given as a vector-valued function of a parameter. So points is now the name of the vector-valued functions, and we're going to plot it from t going from the first endpoint, which is 0, to the second endpoint, which is 2, and we'd like our graph or the curve to be thick and black. Our axis labels are going to be the coordinates, so we write that, and we're going to make the aspect ratio automatic, and we'll see what the effect of all this is. We just execute this, and there it is. What this has done is this aspect ratio automatic ensures that the scales on both axes are the same. If we didn't do that, then Mathematica would choose a scaling which suited it. Notice that the labels, the axes, are labeled with their proper names, and that this looks like an ellipse. A list of assignment rules for assigning the expressions of the coordinates in terms of the components of the vector-valued functions can be generated using this. XY set equals a table, and we want the relevant coordinate, an assignment rule, assigning it to the to the corresponding element of the vector valued parametric function, and we want to do that for each coordinate. Now we know we've only got 2 coordinates here, but in fact in another situation we might have more, so this Mathematica function length is quite useful, because this will be done a number of times equal to the length of the vector of coordinates. So let's execute that, and you can see we've got an assignment rule that any value of x will be assigned this value locally. So let's pause the story.